Tangential variables. Have you ever seen a team of ice skaters perform crack the whip? To do this, they get in a line and they skate around one of the skaters on the end, trying to keep their line straight. The spinning skater that the others are moving around is centered on the axis of rotation. Since all of the ice skaters along the line rotate around by the same angular displacement, they all have the same angular velocity. Even the ice skater centered on the rotation axis is turning around with the same angular displacement and velocity. There's another velocity that applies here, though. You can see that each skater is traveling along her own circle as she orbits the rotation axis. Since the ice skaters stay in a straight line relative to each other, acting as one rigid body, it takes each of them the same amount of time to complete a circle. But some circles have a greater circumference than others. The ice skaters traveling along the larger circles are covering a greater distance in the same amount of time. Distance over time gives us speed, and in this case we call this tangential speed. This is because at any point along the circle of motion, we can draw an arrow tangent to the circle, which will show us the direction of the skater's speed at that time. Remember, a line drawn tangent to a circle is a line that touches but doesn't cross the circle. And when we include speed and direction, we call this the tangential velocity of the ice skater, which is a vector quantity. The skater moving along the greatest circle has the greatest tangential velocity. In fact, the tangential speed is proportional to the distance from the rotation axis. Remember that s, the arc length, is equal to r, the distance from the rotation axis, times theta, the angular displacement, as long as theta is in radians. Speed is distance over time, and the distance traveled by the skater is the arc length she's traveled, so we'll divide both sides of this equation by time. That means that s over t is our tangential speed. Angular displacement theta over time is angular velocity in radians per second, so we can substitute that in. And we've found an expression that shows how tangential speed is proportional to distance from the rotational axis. It also relates tangential speed and angular speed. There's also a tangential acceleration. The magnitude of the tangential acceleration is equal to the change in the tangential speed over the time interval. The change in the tangential speed is the final tangential speed minus the initial tangential speed. Tangential speed is equal to the distance r times the angular speed. Now we'll factor out the r on the right-hand side. Omega final minus omega initial is equal to the change in the angular speed, and the change in angular speed over time is equal to the angular acceleration. So now we've found a way to relate the tangential acceleration to the distance from the rotation axis and to the angular acceleration when angular acceleration is in radians per second squared. So tangential variables are directly related to angular variables. The difference is that the angular variables describe the motion of an entire rigid body, and the tangential variables describe the motion of a single point on the body.